All right, so today we're going to go through the solutions review guide. We're going to kind of breeze through the first page. The first page is a lot of just definitions. There was a lot of vocabulary during this unit, so we just want to be comfortable with a lot of the terms that we use that will be brought up, especially when you're asked questions about certain things. So in terms of the two parts that make up a solution, of course, that is the solute, which is what's being dissolved. Primarily, we use solids there. And the solvent, which is what does the dissolving. In this case, and we primarily use water there as our primary solvent. Molarity is just a quantified value for the concentration of a solution. So when we refer to the concentration, it's the ratio based off of the moles of solute and liters of solution. Of course, there's our molarity equation, making note that the moles have to be in the unit of moles, right? It cannot be given to us in grams. And of course, the volume has to be in liters, not milliliters. So we would have to do some conversions based on what a question is asking us, based on the information given as well. What is dilution? Dilution is just the process of adding water to a solution. We increase the volume in order to decrease the molarity. In this case, we're assuming that the moles of solute, or how much stuff is dissolved inside the solution, is staying the same. And so being able to add a solvent in order to increase that initial volume to a new volume here should then decrease the molarity that we start with. We always start with the what we call stock solution. That's usually the higher concentration at a lower volume, to then figure out how much how much water we would need to add to dilute. All right, and we had talked about dilution being effectively watering down our solutions. And so going off of that, if we have something that's more concentrated, there's more solute compared to solvent. So think of our Kool-Aid lab. The beginning solution that you had was the first scoops that you put in the first amount of water, and then you went and you diluted it. And so there was more solvent. You were adding water that was watering it down, which didn't necessarily change the amount of solute that was in there, but it changed the concentration, because there was now more solvent available to dissolve those solute particles. So that is the difference between concentrated and dilute. And then you can kind of see a before and after here. So same number of particles in each. The smaller, or the less you have in terms of volume, the higher the concentration is going to be. And then you add water. Once you put water in there, it allows the volume of the solution to increase, which then decreases the concentration, because now you can see those moles of solute are spread out a little bit more. So that's a nice little visual there. In terms of unsaturated, saturated, and supersaturated, it's effectively playing off of what saturated is, right? To have something that's saturated in terms of a solution means that that's the maximum amount of solute that we can hold in a solution. And of course, we also evaluate these at temperatures when we talk about our solubility curve. Unsaturated, we can add more and have it all dissolve, right? So that's we'll get into what that looks like on the curve as well. Same with supersaturated. So these are just the definitions, but we'll see the visual here shortly. But that's when you have too much solute present, more than you're able to actually dissolve, which would mean that it would precipitate out. And this is what the precipitate out portion would look like in terms of the two words that we use here for what would happen if a precipitate existed, right? Precipitate is the insoluble solute that remains solid. It falls to the bottom of glassware, and that's why we call it precipitate. Similar to why we look at precipitation outside as falling down. It's a similar root there. And the supernatant, that is just the liquid solvent that is not a part of the precipitate, right? That is the separation there, of course, the remaining liquid, so to speak. Solubility, I like to look at that suffix ability as the ability to do something, and solubility is the ability for something to dissolve. And then, of course, we have our soluble versus insoluble, right? Soluble is solutes that can dissolve, so they have a good solubility, and insoluble solids, of course, do not have solubility. They are unable to dissolve. They remain solid in water. All right, so let's do a couple of calculations here. So, in terms of the equations here, we have molarity versus dilution, right? And so our molarity equation is right here. So molarity equation compared to right over here, the dilution equation. And so in order to be able to effectively use these, you have to know when you need to use each one. The best way I think of is differentiating these by, are you given 2 molarities or 2 volumes at any point, right? Obviously, the dilution equation has V1 and V2, M1, M2, so there's a start and a finish. If there's no start and finish, then obviously this equation is not going to be useful to us. So if you look through these first 4 problems, deal with just 1 molarity or 1 mole value or 1 volume. And that's another thing. If you notice that the unit mole or grams is somewhere in there, then you know for sure we're going to refer to the molarity equation there. So in this case, what is the molarity of a solution in which 10 grams of silver nitrate is dissolved in 500 milliliters of water or solution? And so in order to be able to calculate the molarity effectively, you first need the moles of solute, and you also need liters of solution. Now, in this case, I give you grams and I give you milliliters. So you're going to actually have to do 2 conversions. The first conversion, fairly straightforward. Converting milliliters to liters, you just divide by 1,000. All right, that's what this middle conversion factor is there. And so we have our 0.5 liters, but it's going to be just a little bit more involved to get grams to moles. Remember, you need to use your periodic table to find the molar mass. We have 1 silver, 1 nitrogen, and 3 oxygen here. We're going to add them together, and we get 169.88 grams per mole. Remember, that is the unit of molar mass, which is what allows us to use it as a conversion. So 10 grams of silver nitrate, we could say over 1. And I see that grams of silver nitrate is going to appear on the bottom. That's for every 1 mole of silver nitrate. Why is grams on the bottom? Well, because grams needs to cancel out as a unit. How many grams? And we just calculated 169.88. And that's going to give us a value of 0.059 moles. And so now that we've converted, we can set up our little inventory here. So we have M, we have N, we have V. M is what we're looking for. N is 0.059 moles. Volume is 0.5 liters. And then we go through and solve. So our equation here is molarity equals moles divided by volume. And we have 0.059 divided by 0.5. And that should give us a value of 0.118 molar. Right. How many moles of hydrochloric acid must be dissolved in this many milliliters of water if the solution has a concentration of this? So you see that we have a volume, we have a molarity. We're asked for moles, which is only a part of this equation up here, not the dilution equation. Plus, we're only given 1 volume and 1 molarity. You know, we need at least 2 of one of them, right, if we're going to use that equation. So that's another way to identify. So I'm using the molarity equation again. In this case, the only thing I have to convert is, of course, milliliters to liters. And so I divide by 1,000. Molarity and V. This time I have a concentration value. I have my volume. I do not have moles. And so we're going to have to do just a little bit of algebra here. Right now, my equation is in terms of molarity, so I multiply by volume on both sides to remove it from the denominator there. And so what I end up with is N equals molarity times volume. there. Now it's solving in terms of n, which is what I want. You can also use the triangle, the algebra triangle that we had talked about before to help you out there too. So we have 4.75 times 0.755, and that's going to give us a value of 3.59 moles. Make sure you have units and make sure you show work. All right. What volume of solution in liters? Of course, it's going to be in liters because we are using the molarity equation again, would make that molar solution 5 grams. And we see that we have grams, so we are going to need to do a conversion here. And so we need the molar mass of sulfuric acid, H2SO4, which is 98.09 grams per mole. So my first step is to get grams and convert it to moles. So grams to moles. So I start with 5 grams. I divide by the molar mass, which is our 98.09 grams, and 1 mole on top. And it's going to cancel out grams. I am going to get 0.051 moles. Now I have my inventory that I can set up. So I have a 0.25 molar solution. I don't know the volume. I do know that it is 0.051 moles now that I did my conversion. And now I'm going to use my equation. Now in this case, we're looking for volume. Volume happens to be on the denominator. So we're going to have to go one step. We need to remove it from the denominator to be able to solve for it. And so our new version of this equation kind of looks like this, like we had before. Well, we stopped above because that's what we were solving for. We're solving for volume this time, so now we have to get it by itself. We have to get rid of m, and we do that by doing the opposite of the mathematical operation that's occurring, which is this, in this case, division. So volume is equal to moles divided by molarity. And then we plug in 0.051 divided by 0.25, and that's going to give me I believe 0.204. 0.204, of course, that is liters. Now, if I would ask you in milliliters, that would be your answer from the equation, since the equation uses the unit of the liter, and then you would have had to do an extra step to then convert it to milliliters. Last but not least, how many grams of sodium chloride are needed? So you notice that I'm looking for grams here. I can't get to grams unless I have moles. So really what this question is asking me is, hey, can you first convert to moles so that we can then figure out how many grams that would be using the molar mass of sodium chloride, which is 58.44 grams per mole. All right, so 0.650 liters, 1.5 molar. We can, since we know we're solving for n, we can use the variation of our equation that we solved for n with above. So that is m times v, which gives us 1.5 times 0.650. And that gives us 0.975 moles. But we can't just stop there because the question's asking us about grams, so we need to go, because it's asking us about grams, from mole to gram now in the end. And so now that we have the unit of the mole, we can use the molar mass. In this case, we're trying to get moles to cancel out, so the 1 mole goes on the bottom. Because I want grams in the end, my mass goes on top. And we end up with 56.98 grams of our sodium chloride that we would need to measure out. All right. Now we get into the dilution equations. Now I know that these are going to be dilution equations because I give you a concentration here, and I see that, oh, there's another concentration here. I have 2 concentrations. I need to use the equation that has 2 concentrations in it. Or I can have something like number 15, which has 2 volumes, and then I can take that information and say, oh, 2 volumes. That's the equation I'm going to use. So that's a way that you can know which equation to use. So all of these, I'm going to actually start off with an inventory again. And in this case, what we did was, because we had these variables, we ended up just, instead of using a question mark, it really doesn't matter, but we ended up making one of them x, like you would in algebra class. So all of our unknowns are going to be x. All of our equations are going to be based off of m1 v1 equals m2 times v2. So I'm just kind of front loading that right now, just so that it'll save a little bit of time. I don't want this video to be terribly long, but in terms of the difficulty with this, it's less of the math. It's more of being able to accurately figure out what's M1, what's M2, what's V1, what's V2, and there's some tips and tricks. So something like what you see here, prepare 250 milliliters of a 6 molar solution. That molarity and volume go hand in hand. So whichever one that is, M1 or M2, then the volume is going to be the same, right? And so we know that at least that helps us out a little bit to put it on the right side of the equation, or I should say the correct side. And so just in context, how much in liters of concentrated sulfuric acid is needed? So is needed would cue us to think that that's what we're starting with, which means that this must be M1. So we have 18 molar M1 to start. I'm asked how much of that, so I must be looking for V1. How much do I need at the beginning in order to prepare or come out with 250 milliliters of a 6 molar solution, right? And so that's how we can go through and define these variables, being able to use these context clues to help us figure that out. It is important to note that you do not need to worry necessarily about the unit of volume here, since the unit will appear on both sides. However, you do need to pay attention to what unit is asked of you to find. So in this case, you can do it one of two ways. I give you the volume in milliliters here. So if you use this volume, the answer will be spit out in milliliters, right? It's going to be spit out in the same unit that your volume or your other volume is given to you in. So you could front load the work and you could convert this to liters right away because you want liters in the end, or you can just use milliliters in the equation and convert at the end. I'll just do that since, I have it there. And so to set this up, again, 18 times x equals 6 times 250. This is going to be 18x equals, where am I? 1,500. And then we're going to divide by 18 on both sides to solve for x. X in this case is V1, and it's going to end up with the units of milliliters because that's what my other volume was in, so 83.3 milliliters. But I need to go one extra step to convert it, and so we have to divide by 1,000 there, and we end up with 0.0833 liters. All right, so just an extra step, so just paying attention to what you're trying to find in terms of these units for the volume. But more often than not, it doesn't necessarily matter if you keep it in milliliters or change to liters. In terms of number 15, if I dilute this much of this concentrated solution, so that must mean if I'm diluting it, that must mean I already have it, right? So that must mean that that's what I'm starting with. So there's my V1, and because of that of connector, it is M1 as well. And so we have 0.6 molar. We have 320 milliliters to a volume of this, which is V2, right? Because that's what I'm diluting it to. What will the concentration of the solution be? Now I'm looking for M2. And so 0.6 times 320 equals X times 850. Simplifying both sides, 192 equals 850x, divide by 850 to solve for x, which is M2 in this case, so paying attention to units that'll come out, we end up with 0.226 molar. All right. a good way to check yourself too on all of these is you know what the relationship is between M1 V1 and then M2 V2, right? The whole point of dilutions is to increase the volume. So if I have an increase in volume, then my concentration should go down, which in this case we see prove true. So just knowing the inverse relationship or effect that those variables have on each other. I make 850 milliliters of 0.7 molar nitric acid. If I'm making this, that means that I did not start with it. So this must be V2 and this must be M2, right? That's what I created from something that I started with. So 0.7 molar, 850 milliliters. By diluting a 12 molar stock, so that's what I started with. Remember, stock means initial. That's what you start at the beginning having. I ask you, how much water did you add? So how much water did you add? And so I'm not just asking you for how much you started with. I'm asking, in order to get to 850 milliliters, how much do you need to put into the solution, right? So that means that we are solving for V1, but we have to go an extra step and figure out, well, how much do we have to add to V1 to create 850 milliliters, right? And so we're solved just like we would normally for one of these variables, in this case, volume 1, our initial volume, 0.7 molar, 850 milliliters. Simplify 12x, 0.7 times our 850 is 595. Divide by 12, so x equals, in this case, 49.6 milliliters. Now, that is V1, right? That's how much I'm starting with, but my question asks, how much water did you add? And so all we'd have to do is figure out, oh, well, volume added is equal to whatever volume you end with minus whatever you started with. And so volume added is going to be 850 minus 49.6. And then that's going to give us a volume of 800.4 milliliters. And you can write added. All right, so just paying attention to exactly what you're looking for there. And last but not least, in the dilutions in this calculation set, if you add 45 milliliters to 300 milliliters of that molar solution, so because of this connector, I know that these two go together. If I'm adding water to that, that must be what I'm starting with, so that's M1 and V1. So I have 7.5 molar solution, 300 milliliters of that. You're going to be tempted to say 45 is M2. That would be incorrect because you are adding that amount to 300, which would mean that this should be 300 plus 45, which would then give you 345 milliliters, right? So just, again, paying attention to wording here. Here we're adding the amount. And then we're looking for the new concentration, so M2 question mark. All right. And so we plug in what we got, 7.5. 300 on that side equals x times 345 after I add the 45 mils. We end up with 2,250 equals 345x divided by 345 divided by 345. X, which is M2, so my unit should be molarity, is 6.52 molar. All right, so hopefully those are some tips and tricks for all of those types of problems and being able to rearrange equations or solve for one thing and just making sure you're paying attention to detail in terms of what you're being asked to solve for. In terms of our solubility curves, remember that the grams of solute appear on the y-axis here, so that's how much of those substances we're trying to get to dissolve. And these are the temperatures at which we're dissolving them at. What we notice is as temperature increases, the solids are more soluble. There's a direct relationship there, right? And so the solid lines here for the solid substances all increase. And then the opposite is, as temp goes up, the solubility of gases go down. That's an inverse relationship. And so we notice that with hydrochloric acid here, and if it's gaseous, ammonia, sulfur dioxide, right? And so we see that all of those gaseous substances, they actually decrease in solubility. Think about carbon dioxide, which is a gas. Again, we talked about in class why pops and other carbonated beverages go flat, because the carbon dioxide gets less and less able to be dissolved in that solution as it gets warmer. So just a little practical application there. So how do you read this? Well, there's a couple of ways. We can come back to our unsaturated, saturated, and supersaturated, and note that if we are comparing an amount of solute at a certain temperature for a certain substance, then what we can do is we can take a look at where that point exists, and if, because this would be the saturation line, in this case we're talking about KCl, and so if this is the saturation line as the temperature goes for each of those temperatures, then I can identify if I have 60 grams, so 60 is right here, I am going to match up 90 and 60 and put a point there. And what I see is that the point that I have is above the saturation mark, which means that because it's above the line, this would represent what we would call a super saturated solution, right? And it's super saturated. Therefore, what I can also do is say a follow-up question, and I can say, well, if this is saturated, right? If on the line is saturated, and let's say, I don't know, let's say it's about 55 grams. Well, I can ask you, since it's supersaturated, how much would precipitate out? So I take how much I have, which is 60, and I just subtract what the saturation would be, and I would know that 5 grams would precipitate out. So those are the types of questions that you could be asked regarding the saturation of these substances there. All right, but what I would highly recommend is marking up your curves. You will have a curve on your exams so that you can actually mark up as you need. 35 grams of KClO3, if we do the exact same thing we just did, you should end up with the point on the line, which means that it's the maximum amount that it can hold, which means that that is saturated. So that is the, some of you in class said it's the perfect amount, or whatever the case might be, and you can think of it that way. So how many grams of solute can be dissolved? So in this case, remember, all values on the chart are based on 100 grams of water. That's our baseline amount of water that we're using. So just know that if it ever says 100 grams of water, you can kind of just ignore it, knowing that the chart shows all of these masses based on that. And so I'm just kind of looking at where those lines are hit at these temperatures. So for KNO3, which is this line right here, if I'm looking at 40 degrees, I would just take 40. I would go all the way up until I hit that line, which is right about there. And I mean, roughly, we can say that that's about 65 grams, right? If we were to go over here, it's about halfway. So I would say 65 grams. And so if we're talking about how much can be dissolved, or what the solubility is at certain temperatures, all we are looking for is where at that temperature does it hit the curve of the substance that we're looking at. So for these other ones, you should have gotten around 39 grams as well as 124. Again, there's going to be a little bit of leeway there too. In 21, what you notice is there's a difference in the amount of water that we're using here, and so I want us to make sure that we note to set up a proportion, because remember, we just said that the chart gives us values that can be dissolved in 100 grams of water at certain temperatures. Now we're talking about 285 grams. And so what I like to do is I like to identify the temperature that you're looking at, and you don't do anything with that other than that's the temperature that you look at. So we're really just focused on whenever the substance hits that line at that temperature. That's all that means. And so what I need to do is I need to identify how much does the chart tell me I can dissolve in 100 grams of water. I'm just going to put H2O there instead. And then I can say, well, then how many grams would I be able to dissolve in 285 grams of water? And so what we're doing is we're setting up a proportion based on how much we can figure out dissolve in 100 grams at this temperature. And so this value right here, this is the only one we're missing, we're going to base off of the KCl line because that's the substance that it's asking me about. And I'm going to take that 10 degree mark and I'm going to go all the way up until I hit KCl to figure out how much can I dissolve at 100 or in 100 grams of water at that temperature. And I see that I can dissolve 30 grams. And so if I can dissolve 30 grams in 100 grams of water, then I can figure out X, how much I can dissolve in 285. So anytime we have a changed amount of water, we can set up a proportion this way. And all we have to do is cross multiply to solve it, right? And when you cross multiply, what you end up with is on one side of the equation, does not matter which one goes first. I usually like the X first, so 100 times X equals 30, and we can do that in the calculator, 30 times 285, which ends up being 8,550. And of course, when you're dividing by 100, you're just moving the decimal back 2 spaces. So I can actually dissolve 85.5 grams of KCl at 10 degrees, mind you. But I can dissolve that much if I had more water, specifically 285 grams of water. All right, next one up. I'm looking at 22, and it's talking about KNO3, so I'm going to identify where the KNO3 line is. In this case, that is this one right here. And so that's the line that I'm paying attention to. I have 60 grams dissolved in 100 grams of water. Well, we know that it's 100 grams of water, so if you want to just kind of cross that out, we can. At 50 degrees Celsius, so I'm looking at 50 degrees. So here's 50 degrees, and then I have 60 grams here. And so I'm going to go up until I match those 2 points. And here's my plot. And now what I notice is it is well below the curve of KNO3. And because this is below the curve, it is unsaturated. And so what I would say is, let's figure out how much I can dissolve at that temperature in order to then figure out how much more I'm able to add, because that's what the question's asking me there. So I would say at 50 degrees Celsius, a saturated solution holds, and then we see how much would a saturated solution hold. A saturated solution is on the line, right? On the line. So here's us, right? Think of it as a map. You are here. And now we are trying to figure out, well, how much more can we add until we get to here, right? How much can you add? And so all we have to do is compare those 2 points. Really, we're just taking the greatest number and subtracting the smaller number. And so in this case, this is about, I don't know, let's say 85. So I would down here say a saturated solution holds 85 grams. So 85 grams minus the 60 that I notice I have allows me to know that I can add 15 grams, right? I can have 15 grams worth of potassium nitrate to add until I become saturated at that temperature. So again, if you're under the line, you're just subtracting the saturation mark red from the purple mark, which was under. The same thing applies for the supersaturation as well. At what temperature does potassium iodide have a solubility of 140 grams? That's just 50 degrees Celsius, 15. Again, we're just looking at where does that hit. Here's potassium iodide. Here's 140, so we mark that. Now we're going down, seeing what temperature that would be at. It's about 15 there. All right, we have 130 grams of potassium nitrate at 60 degrees Celsius. How much solid will precipitate to the bottom of the container? And that's because this is supersaturated. So this was unsaturated. This one is super saturated because there's going to be a precipitate that forms. And so we look and we do this very similar to how we did before. Good thing we are on the same substance here, potassium nitrate. And so here's potassium nitrate. I'll just re-highlight that. Get rid of all the extra stuff. So we're saying that we have 130 grams, and so this is 130 grams, at 60 degrees Celsius, and so let's match that point. So here's 60 down there, here's 130 up here, so I'm going to keep going, right? And that's that point right there. And so what I know is that because this is my line, right? Because this is my saturation line, at that temperature, I can only hold as much as it can when it hits the line, right? So really, I can only hold 110 grams. But I'm telling you that I'm trying to put 130 in there. That's not going to work at that temperature. And so what I do is very similar. I say, well, how much will precipitate out, right? How much will fall to the bottom of the test tube because we have too much? And I do the same way. I say, well, at 60 degrees Celsius, a saturated, so on the line, solution holds 110 grams. So 130 that I have minus the 110 is going to tell me that 20 grams will precipitate. All right, and there's that. All right, and the last one. This is a very similar one to number 21. We are taking a proportion since we have the 75 grams of water instead of 100. We're evaluating at 50 degrees. So at 50 degrees, all that tells you is that's the temperature mark that you're looking at. So I need to figure out from the chart how much can dissolve in 100 grams of water at 50 degrees in order to then figure out, well, how much can dissolve in 75 grams of water at 50 degrees. So that mark here is going to be from the chart. So I go up. I'm talking about ammonium chloride here, which is NH4Cl. And so let me get rid of all the extra stuff here that we added for the others. Here's ammonium chloride. And I look at 50 degrees. 50 degrees, I go up. And I can dissolve about 50 grams there, right? And so 50 grams at 50 degrees, I cross multiply. And you end up with 100x equals 3,750 divided by 100 divided by 100x equals 37.5 grams. And so makes sense. I have less water. I'll be able to hold less solute. All right. So next up, here's just a couple of examples of formula writing. Remember, for our net ionics, we are using ionic compounds. And so barium phosphate plus 2, phosphate minus 3, barium, being a +2 charge and phosphate being a -3, we need to cross those numbers. And so my correct formula for this is Ba3PO4. I can get rid of those charges up there once I get the correct formula. Now, we're using the solubility rules. I will pull up here really quick just to give you a little refresher there. The solubility rules are right here, where if you want to take a quick screenshot of this or screen grab, you can if you're on your iPad. But in terms of the solubility rules, you have them on your periodic tables as well on the backside. These are the things that tell us whether something is soluble or aqueous or insoluble. And so can dissolve means AQ. That was an awful Q. For aqueous, cannot dissolve means solid for precipitate. So those are the rules there. So based on those rules, I go back here and I identify that barium phosphate, according to Rule 6, is insoluble. Copper 1 nitrate, copper 1, that means that this is a +1, nitrate's a -1, CuNO3, right? That 3 is a part of that group, just like this 4 is a part of that group, and it doesn't tell you how many. It doesn't say that there's 3 nitrates or there's 4 phosphates, right? Just, again, a little bit of review. Rule 2 states that any nitrates are soluble, all right? So that is AQ. Sodium phosphate, -3. So sodium being a +1, phosphate being a -3. Crisscross those. I only need 3 sodium for every 1 phosphate group. This is actually soluble. The other phosphate was insoluble because it was attached with barium. And remember the charge discrepancies there, right? The 2 and the 3 provide a stronger force of attraction between each other. But because sodium is an alkali metal, alkali metals are always soluble when they're with a partner. So that's another, that is Rule 1, kind of mixed with Rule 6, because Rule 6 also tells you that phosphates are soluble when they have something that is an alkali metal. Potassium's an alkali metal as well. So the same thing happens down here with the potassium hydroxide. That is kind of based off our solubility rules. So home stretch, we're almost through. So in this case, what we want to do is we want to take those equations, and I'm going to put the ion charges above everything, just because that usually helps me keep them together and know that that I'm not going to necessarily have to have the same number of atoms or ions in a formula on one side of the equation as I will the other. So barium nitrate, the +2 and the -1 is going to cause me to need 2 nitrate groups. It is always going to be aqueous for our reactants in these problems. Potassium sulfate, K2SO4, because again, crisscross those charges there. And then we get to barium sulfate, BaSO4. That is going to be our solid, and we have to figure these two out. So these you identify. Oops, here's what I wanted to do. Identify state of matter each product is based on your solubility rules, right? So we know that we have aqueous reactants in all of these double replacement reactions. We have to use our solubility rules to figure out which one's solid, which one's aqueous. Potassium nitrate here is aqueous based on our solubility rules. And then we go through and we have to make sure we balance, and we should only need a 2 in front of the potassium nitrate there. And so in the space below, we're going to write the complete ionic equation. So just remember that all aqueous compounds dissociate or separate. So all aqueous compounds dissociate or separate, I could say, into their separate ions. All right, and so anything I see that is aqueous, I'm going to split up into its ion. So in this case, barium nitrate is aqueous. It's made up of a barium ion. And because it's aqueous, the ion is aqueous as well. And 2 nitrates, right? And so that 2 tells me I have 2 of those nitrate ions, noticing that I'm including a charge and state of matter for all of this. Potassium, there are 2 potassium ions in that formula, and there is 1 sulfate ion in that formula. And that is going to produce a solid insoluble product, which doesn't split up. And we have 2 potassium ions on this side because of the 2 in front that we use to balance the others on the other side, as well as 2 nitrate groups. So you see how balancing the equation also helped us balance the amount of ions there. That's what balancing does. And so I want to cross out all spectator ions. What I'm going to do is I'm going to identify the solid precipitate, and then I'm going to note which ions on the reactant side are a part of that. And I notice that it's the barium and the sulfate ions. And so the spectator ions are the ones that just watch everything happen. Boom, boom, boom. They don't participate. And so what's highlighted and what's left over is our net ionic equation, right? This is the what truly occurs when we mix barium nitrate and potassium sulfate together. This is the actual occurrence here. So we have our aqueous, and then of course we have our solid product. All right, and again, you need to make sure that you're aware of us. Whoa. You need to make sure that you're aware of us including the charge on all ions that are separate and the states of matter on every ion, as well as our solid precipitate. So a lot to remember, but again, it gets a little bit easier as you kind of get into the groove of this. So by doing the exact same thing, in this case, I give you those formulas, so I just want you to identify which one's aqueous, which one's solid. Aqueous, this is solid based on our solubility rules, and so anywhere it's aqueous, we have to make sure that we dissociate. So there are 2 sodium ions that'll come apart because they were attached or attracted to 1 carbonate ion. And then there's 1 calcium ion that had 2 fluorine ions, or fluoride ions to be a little bit more specific, attached to it. And then, of course, we have the 2 sodium ions up here on this side with the 2 fluoride ions. And we have our calcium carbonate solid that does not dissociate. And so, again, I can look at what's the precipitate that's formed, what are the ions that form it. Everything else is a spectator, right? Everything else is just watching the show. And so I like to, even though it's in a different order, I like to put the positive cation ion first always, because that's what our formulas do. And we have our carbonate ion there. And we end up with our solid precipitate. All right, so hopefully this helps. Just remember that if ever I end up with 2 aqueous products, and I'll show you kind of that real quick, 2 aqueous products, right, everything breaks apart and there is no reaction because everything is dissociated. There are no solids formed. So that's just something to kind of be aware of too. But again, hope this helps. A little long as usual for a lot of these keys for the review guide, but it is a lot to kind of put into one. So just use what parts you need. And again, hopefully this helps, and I will see you all later.